In Spanish, this will be autómatas finitos. And of course, lenguajes regulares. Regarding the word automata, please take into account that when we speak in English, we say automata to refer to a plural, automatas. And if we want to use the singular word, then we will say automaton. Because this is a word derived from Greek, so we are still using the plural from Greek. Automata, automaton. Well, the plural from automaton is automata. Okay, but in Spanish it's normal. It's automata, and the plural is automatas. Okay, so this is plural, and this is singular. Just an observation in case you have any doubt. So here we will see the first one of our machines, which will be able to represent a language. We will see how will be done. For this task, we will have a diagram, or we will suppose that there is a machine that has an infinite tape like this. This tape is infinite to the right, but not to the left. And we have a head here, which is able to read, only read, the symbols that are placed on the tape. A, B, A, B, etc. Cells can be empty as well, and usually there is a mark of end of string. So the thing here will be called string, cadena in Spanish. Each one of these is called symbol or símbolo. And for the machine, we will represent that it is on a particular state at a time by using something that looks like a clock face. Not because we are measuring time at all, nothing to do with this, just because we want to denote that there is a particular state present at any time, just one state. So currently we are on state 1, but we could be in state 2, 3, 5, etc. And there can be a large number of states, but always a finite number of states. Of course, this machine is a bit old because it's still an analog phase, but it could be digital. So this is just a representation, not really a part of the machine. So this is the conception, the general conception of the machine. And now we will see how is the diagram of a machine of this. For example, suppose we want to recognize what makes a good variable name. So all of us, or most of us, are programmers. So we want to recognize when a variable is correct, when the name of a variable is correct. So we write something like this diagram, and we say this is letter, and this is digit. And once we begin with letter, then the rest of them are correct until we finish our string, or token in case we are thinking. And finally, digit, we fall into this part. So we can think of variable names. For example, if we say var1, variable 1, or variable 2, or the famous foo or var, which are classic ones, are okay with them. But what if we say, for example, 1, 2, var? This is not a correct number, a correct name of a variable. So we are trying to see which one of these names is correct for a variable or not. Yes, estamos tratando de ver cuáles son los nombres adecuados para una variable y para ello estamos realizando este diagrama que tenemos aquí. Queremos decir var1, var2 son nombres correctos de variables, pero cosas que empiecen con número como 1, 2 var no van a ser nombres correctos de variables. Entonces, para ello vamos a utilizar este diagrama que tenemos aquí. Vamos a empezar a procesar cada uno de estas cadenas. A este vamos a llamarle cadena. Cada una de estas va a ser una cadena, ¿no? Cadena, 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 string, cadena, cadena, cadena. Y cada una de estas cadenas está formada por símbolos. Esta cadena tiene 4 símbolos, esta también, esta tiene 3 símbolos, esta tiene 5 símbolos. Okay. So once we have this, it's as if we had here, oh, too big. Let's make it smaller. So let's suppose we have here in our string, on our string, something like VAR1, and my head is reading the first element of the tape. And simultaneously, we are in position of the first state. So we are here. At this point, I have the option when I read a letter, then I know I need to change from this state to this one. So this will be state 3, and this is state 2. So when I read this letter, I know I have to change my current state from this to this, and now my new state will be 3. Now my machine is in the state number 3, and I have advanced this head to this part of the tape. Or maybe it's easier just to think that the tape is advancing, the tape is moving, right? So, but if I draw this, it will be even slower. So I am moving the head of the machine. So once we have reached this third state, we have the same, we keep reading letter, 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 digit. And when I finish reading this string, I will stay on an accept state. You can see that this state is different from the others because this is double circle. Double circle means an accept state. A machine like this one can have more than one accept state. Let's suppose we could have something like this, or even all accept states. This is not the case, but we will see other machines like this, or even there are machines that have no accept states at all. We will see how they behave in the following examples. For now, what we want to know is that, okay, if I have bar 1, bar 2, or foo, or bar, I know I will end always in an accept state. However, if I start with 1, 2, var, something like this, then it would be as if I was trying to read here 1, 2, VAR. My head is reading the number 1, and at this point, I will again be at the state number 1. I'm heading for the state number 1. I'm here, I'm standing here, and then I read a number, a digit. Sorry, this is a Spanish letter, dígito. I'm sorry, it should be digit, right? Okay, so I am reading, I'm standing here, I read a digit, number 1, then I move to state number 2. Now I am at state number 2. I am here now. And I read the next one. Now I'm standing here. So whatever happens afterwards, I will never reach an accept state. There is no way I can reach this accept state. So of course I need to finish reading the string. So there will be something which is called implicit state. The implicit state looks something like this, which says whatever symbol it comes afterwards, letter or digit, you will never come out of this state. It's something like a pit. Es como un pozo. un pozo del cual no vamos a poder salir, porque una vez que llegamos aquí, cualquier cosa que venga, ya sea letra o dígito, nos va a llevar a este estado y vamos a seguir leyendo la cadena hasta terminar de leerla con letras o dígitos y me voy a quedar aquí en el pozo. Entonces, cuando se termine de leer la cadena, no voy a terminar nunca en un estado de aceptación. ¿Qué pasó aquí? Esta parte azul yo no la había dibujado. Esto se llama parte implícita del diagrama. No se pone de manera explícita. Entonces, eso quiere decir que cuando no diga qué vamos a hacer, en cualquier momento, supongamos que aquí no dice qué hacer con letter y nada más dice puro digit, digit, digit. Entonces, inmediatamente vamos a asumir que si llega una letter, nos vamos a ir al pozo. ¿Sí lo ven? So you can see that for every arc that is not explicitly defined, it means that it will move us to the pit. In this case, I erased letter. So if I do not put it explicitly, it will always lead me to the pit. And there is no way to come out from this pit. This pit is usually never drawn because it's implicit. Yes, so every time I have something that does not say where I am going to, it means it will go to the pit. Don't worry, there will be more examples on this, a lot more examples. Now we are still on the introduction on how this machine works. So now let's think of a different machine. This machine was sort of a token recognizer machine. This will recognize a token for a compiler when you have to recognize when you have a correct variable name or not. Now let's think of a different machine. How about a soda vending machine? Probably you have used them, you know them, are those that have something like this. I'm very bad to draw, and it's better if it says the brand, but I didn't want to make an advertisement, so maybe you want to drink Pepsi, if not Coke, or better don't drink sodas at all. Okay, but anyway, you have to, you have a value here, let's say 3 pesos and 50 cents, or $3, which I know that 3 pesos is very cheap for a drink, but this is the value that drinks had when I was studying at ESCOM. So it's a retro reference for those times. Yeah, it was 1994. So you have to deposit coins, coin by coin, until you reach this value, right? And then the Coke or the soda you want comes out. A little beautiful, refreshing, and delicious soda. Yeah, sorry for the advertisement, but it can be any other kind if you want. Okay, so maybe I'm thirsty, right? Okay, so now we can draw a diagram for this machine. Now our symbols, and now I will introduce the name of this set. This set sigma, this is an uppercase sigma, Greek letter, will denote the different symbols we can use. In the previous cases, we had something like sigma is A and B, or in the case of the variables, sigma are the letters and digits. Now, our sigma will be made out of coins, coins of 50 cents, and more scarce, but still there are coins of 50 cents, and 1 peso, and 2 pesos, and okay, let's make 5 pesos. And that's it. Of course, there are 10 and more coins, but we will restrict to these coins so that we don't have a very complex diagram. So this is our inventory of coins, which will be the symbols that will form the string. The string will be valid whenever we reach the value of a Coke. the value is 3 and 50. We will start, always remember to draw this arrow. This arrow means the initial state. So always, when you are drawing an automaton, please remember to draw this starting state. So we start with 0 pesos, and we have several options. If I insert 5 pesos, then immediately I have reached the correct amount for a Coke or for a soda. Then it's an accept state. Why? Because I have surpassed this value. I don't need, and it doesn't need to be exact. If there's more than the value needed, it will just give me the Coke and it won't give me change. This machine doesn't give you change. Yeah, so it's a bit of a thief machine, but don't worry. Okay, so 5 pesos, I have my Coke, I have no change. Okay, next. What happens if I insert a 2 pesos coin? Okay, I will have 2 pesos. Still no accept state because the correct value is 3 and 50. And if we continue with the different values, well, you know what will happen, 1 peso. And finally, we have here 50 cents. And in this case, we will have 0.50. Now you are getting the mechanics, I think. For 2 pesos, for this state, now I will do the same. What happens if I insert, and this is wonderful for the company. The company is very happy if I insert 2 pesos and then 5 pesos, because they will have 7 pesos and give me just 1. It won't give me 2 Cokes, no, just 1, just like real machines. And no change, again, no change. Okay, so it's an accept state. Why? Because I added 2 and 5, now I have 7. This is just a tag. Here, these names are just tags. I can name this state A, B, C, D, E, F, or any other number, and it still works the same. The important thing is that the symbols here should be corresponding to the coin I'm inserting, right? Okay, so now if I insert a coin of 2 pesos, I will have here, again, an accept state. Why? Because now I have 4 pesos. Please note that now I have used all different coins here. So we have finished for this state. We have finished considering all different options. Now, now we will not continue with the accept states because I have my Coke already. So I don't need to keep inserting coins. So in this case, for this machine, all these accept states will be end states. It's not the same. Later we will see, or as in the previous example, we will see for some machines that I reach an accept state and then something happens that takes me out of this accept state, maybe into a non-accept state. So accept states are not final states. It's different. But for this machine, for the soda vending machine, all our accept states will be final states. For this example, yes, this will happen. Okay, so once I have this, now I will work on this state of 3 pesos. And we will see something interesting. I will change color so that you can see the new the new arcs I will be drawing. Arc is this is an arc. Estos se llaman arcos en español. Arcos, in English, arcs. So I will draw arcs with a different color. Now, what happens if when I'm here, 3 pesos, I have 5 pesos? Well, again, the people of the company will be very happy because now we will have 8 pesos just for 1 can. But anyway, is an accept state. Okay, here we are again. So I had already this 3 plus 2 pesos, it's 5. So I have already state, I don't need to repeat it. The same will happen for 3 plus 1. So I will just connect with this one. And finally, 3 plus 50 cents will give me 3 and 50. And it's an accept state. And I have finished for this state. Now, for this one, I'll do exactly the same. I will go a little bit faster, but if you have any question, please let me know, and I will slow down. So the same for this one. If I have a coin of 5 pesos, now I have know that this is also an accept state. If I add 2 pesos, then I will have 450, and again, accept state. And for 1 peso, I have already drawn this state, so I will have 350. And finally, if I have just one coin of 50 cents, I will go back to this one just to complete 3 pesos. And I have finished for this state. So I have 2 more states to go on. If you want, you can work on your workbook, or no, it's a cuaderno. I forgot the word for cuaderno.
Notebook.
Notebook, yeah, thank you. So please complete this diagram on your notebook, and when you finish, show it to me on the camera so that I can see it. if you finish, please remember to show it to me on the camera so that I can see your work. Well, I hope I can see. Okay, Maraya. Give me a second, Sarah. I'm just trying to see the one of Maraya, but it has very low resolution. Let me, wait. Keep it there. I will try to focus only on your, yeah, good. I can see it very good now. Okay, yes, you got the idea. Very good. And please, Sarah, go ahead. Okay, so now you are reusing a lot of states, previous states, right? Good. Cesar, please. Okay, very similar. Yes, good. Emilio? Okay, so you try to avoid stepping on other arcs, which is okay, very good. And Byron, please. Okay, let me see it bigger. But it's not complete yet, right? Okay, so let's move on. You can complete this at home, but you are already at home, right? Well, but you can complete this later. Well, because we are used to say that, right? When we are on the classroom, we say, actually, everything we do is homework, right? Okay, so let me write the definition of the formal definition of an automaton. So this is the formal definition of a deterministic finite automaton. This is, it's very important to notice that it's deterministic because at every point we will have only one and only one option. This means that if we have something like this goes to this state and this goes to this state. This is deterministic. Non-deterministic will be when, for example, we have something like this and also with B, we go to this place. So if we are standing here and we need to, we have an A, there's no problem. We know we will move to this state. But what if we are standing on this state and we need to, and we receive a B? We don't know, here or here. So this is called non-determinism. We will explore this kind of automata in the next classes, but for now, we are learning the deterministic finite automata. Yes, and it is finite. Why? Because there is only a finite number of states. You can have 1 million states, but the set of states should be finite. An automaton, because it will move by itself, just to put it some way, it will be automatic depending on the input receiving. Quintuple, this is the quintuple here, which is composed by 5 elements. And these 5 elements are S, the set of states. So if we name the states 1, 2, 3, 4, we can say that S for this case, no, sorry. Let me put the examples on a deterministic one. Otherwise, we will be doing something different. Okay, so let's draw the original one. Let's suppose it works very simple like this. Okay, so S for this state is 1, 2, and 3, and that's it. The next element is sigma. You have heard of sigma before, and sigma is the number, the symbols, the different symbols this automata is accepting. For in this case, A and B. For other automata, there are C, D, E, etc. In this case, only A and B. And then we have this delta, which is called the transition function from S cross sigma to S. And this means, remember that if we do S cross sigma, it means I can choose an element from this set and a second element from this set. So for this case, we have, if we are standing on state 1 and I have an A, then I will end on state 2. However, if I'm standing on state 1 and receiving B as input, I will finish at state 3. So this is the delta function, delta transition function. So you can see it's exactly the same as drawing here, or I can specify here by using the transition function. There is another element called iota, which is like an E, an I, but without head. So we just remove the little point, and now we have a iota. And is the initial state. There will be only one initial state always. So in this case, is this one, and we can say that iota is equal to 1. Because it's just an element, we don't need to make a set for this. And finally, F is a subset, is the set of accept states. In this case, I have only one accept state, which is 3. We can have, as we said before, we can have 2 or more accept states, or none if F is a empty set.